Hey y'all, it's Miss Johnson. Today we're talking about exponential equations. We've got a assignment to do, which is for exponentially either growing or decaying situations. We're going to write equations for them, and then we're going to use those equations to do some stuff. So let's first, I'm going to re-go over what exponential equations are, the basic one, then the growth, and the decay. We're going to come up with ways to write these formulas, and then I'm going to do an example about me liking iced tea. So let's get into it. Exponential equations, we talked about this last Thursday, I think. Exponential equations are ones that look like y equals a times b to the x, where a is your starting point. So this kind of reminds us of the starting points for y equals mx plus b. The starting point, it's when x equals 0. So this is technically the y-intercept as well. That's just a fun fact, though. And then this b is what we're multiplying by. To get from one value to the next, right? Exponential equations are like when we take a number like 10 and then multiply it by 2 a bunch of times. So 10, 20, 40, 80, etc., right? Or we take a number like -7 and multiply it by 1.394. They don't have to be nice numbers. But the main thing is linear equations, when we have a straight line, you're adding the same thing every time. Whereas exponential equations, you're multiplying by the same thing every time. Cool, so that's the basic exponential equation. And now we're going to talk about two specific types, which is growth and decay. Growth is when we're multiplying by a number bigger than 1. So this number's, the value is getting bigger and bigger and bigger, right? We're growing. And then exponential decay is when we're multiplying by a number smaller than 1, but bigger than 0. And that's like you're multiplying by a fraction, so it's getting smaller and smaller and smaller. All right. For exponential growth, this is called the principal, and this is also the principal, right? And it is, again, our starting point, what value we start at. This R, let me make it other blue. This R and this R is the rate of change. Here, it's the rate of growth, written as a decimal. And here it is the rate of decay, also written as a decimal. And together, this 1 plus r and this 1 minus r just become the number we're multiplying by, right? So far, these are kind of the same equation. This t on both is time. We're just saying whenever we plug something in for x, here we're calling it t because it's always time. It can be minutes, seconds, years, kind of whatever the problem is talking about, right? And then finally, what we're finding in these growth and decay is the total value, right? So the starting point, we're actually going to call it the starting value to make that look nicer. And this is value. And again, I always post these notes on the Schoology page, so if you want to have this copy while you're watching the video or when you're doing homework. Okay, so exponential growth, again, you start with what you start with. You multiply by 100% plus the percent that you're adding, and then you take that to the power of time. Whereas decay, you start with what you're starting with. You multiply it by 100% minus what you're decaying by, and then you do it for whatever amount of time you're doing. Actually, I should have had this as well. I want to go over some percentage stuff just for funsies. And then we'll do this. Bada bing. I'm getting faster at that, y'all. Okay, so percentage review. We want to take something that's written as a percent and be able to change it into a decimal, right? So things like 50% or 23% or 87%, changing it into a decimal is semi-straightforward. We just say 0.50, 0.23, or 0.87. You just write the percent with the decimal in front of it. Bingo bongo, right? The tricky ones are actually the smaller ones. When we say like 3% or 7%, or even like 5.1%, right? This is, I think, the hardest one of all of them. Whenever we have single digit numbers, we don't want to write 0.3 because this is 30%, right? What we want to write is 0.03 for 300ths, 3%. So 7% would be 0.07, right? And then the one that's wacky is 5.1% becomes 5% would have been this, and we add a 1 on the back. So 0.051 is the same as 5.1%. So that's just something we want to mention, because when we're using these equations, when we plug in the R, we're using the decimal version, right? And we had talked about this right here and right here. We want to always write them as a decimal when we're plugging these in. All right, let's do an example. Here is the scenario we find ourselves with. Ms. Johnson loves iced tea. It's true. She also loves having her heater on in the winter. Also true. I'm a very cold person. At 9 a.m., when class starts, my drink is 40 degrees Fahrenheit, but it's rapidly heating up. The temperature increases by 5% every hour. If you have a little thermometer in my tea, it's getting hotter. So we've got two types of questions we can ask about this situation. Y'all, first we need to make an equation. So first question is make an equation for this situation. Boom. And then afterwards, we've got two types of questions, right? Okay. So make an equation for the situation. We're going to use exponential growth because the temperature is increasing, right? So we're going to say it's y equals, so total value of the temperature equals 40 degrees. That was my starting point. Times 1 plus 0.05, because this is my percentage increase, to the power of t, where t is hours, right? And the unit for y is degrees Fahrenheit. Again, we started at 40 degrees, we increased 5%, so we did 1 plus 5% in a decimal form. We talked about this in class, where you're allowed to simplify any math anytime, basically. So I'm going to say 1 plus 0.05 is just 1.05. And then when I'm doing my calculations, I'm going to use this version of the equation because it's nicer. All right, now that we've got our equation, we've got two main types of things we can ask about this, which is if you know the time and want the temperature. So how cold is my drink at noon? We know the time is 3 hours after 9 a.m., so time equals 3 hours. And I want to find the temperature. So I'm going to rewrite my equation, but plug in a 3 for t. And then I'm going to go in my calculator. You can use Desmos or whatever you want. I'm going to say 40 times 1.05 to the power of 3. And it's going to say 46.305 degrees Fahrenheit. This is how warm my drink is. And by warm, I mean cold. And by cold, I mean that's the temperature. Again, when we know this and want to know this, we plug in the t and we solve for y. The other thing that can happen, which I think we talked about a little bit in class, is what if I know the temperature but want to know the time? All right? Similar. I'm just going to rewrite the equation, but I'm going to plug in 50 for the thing that I know. All right, nice. And then you might say, Miss Johnson, how am I possibly going to know what t is? Right? There's two ways to do this. We can either guess and check, right? We already know it's going to be bigger than 3 because at 3 it was 46 and I want it to be 50. So we can guess and check t equals 4, t equals 5, t equals 6, 6, and then keep going, right? That's like the way we're going to do it now. And then eventually we'll learn how to use something called logarithms, which is the inverse of exponentials, and we'll just be able to solve this using PEMDAS. But for right now, what happens if we try to solve this using PEMDAS? We say, oh, we divide each side by 40. Nice. That cancels. We get 50, those cancel. We get 5 over 4, which is 1.25 equals 1.05 to the power of t. And then to get rid of t, we don't take the square root. That doesn't cancel. We can't divide, we can't multiply, we can't add or subtract. It's like, oh my god, what do we do? What we end up doing is we take the log of both sides, which is something we don't know how to do yet, which we'll learn in Algebra 2. But for right now, we're just going to guess and check and figure out what's what for what. So when I plug in t equals 4, let me go back to my calculator. I'm going to plug in 4. I get y equals 48.62. So that's not quite it because we're trying to get to 50. When I plug in 5, I get that y equals 51.051. So it must mean the time is when t equals 5, which is 5 hours after 9 a.m., which is 9, 10, 11, 12, 1, 2, which is 2 p.m. So halfway through office hours. And now the question becomes, does this equation make sense forever? And then this is just a fun fact that we're doing on the video call right now. You won't have to answer this type of question on the homework. But does this make sense forever? No. Right? Because if I leave my drink out for a day, so 24 hours, this equation says that my drink will be 129 degrees Fahrenheit. And my house isn't that hot, right? My house is about 80 degrees Fahrenheit. So my drink isn't going to get hotter than 80, right? There's a ceiling, a limit on how hot my drink can get if I just leave it out and don't like boil it. So no, this equation does not make sense forever. My drink will not heat to 129 degrees if I just leave it out. For 24 hours. Right? So this is kind of the trap, or like the complexity of using math equations to kind of like model real life equations. Real life is pretty messy. Real life is pretty complicated. So like maybe it increases at 5% per hour for the first 10 hours, but then it like tapers off. Or like maybe there's outside effects. Maybe I keep adding ice to it. So it's nice to have like an initial equation that makes sense, but we have to recognize that sometimes these math equations just make sense for like hours 0 through 10. And like we have to restrict the domain is what it's called. We have to like zoom in and say like, this is what it looks like for this point in time, not just forever. Like you can't just plug in 1,000 and then this is like superheated. But this last purple equation is just kind of a fun fact. These three, writing the equation, using them to find the total value, and then using them to guess and check for the time, those are what we're going to be doing for our homework. If you feel like you need help with that, email me, come to office hours, reach out to your friends and your classmates. Otherwise, let's get to getting. All right, I'll see y'all on Monday.